Hi everyone, I'm Xitong Liu, and I'm excited to share our work on combinatorial logistic bandits, a joint project with Xiangxiang, Xuchuang, Mohammed, and John at UMass Amherst and COHK. And our goal is actually to tackle complex online decision-making problems in systems like content delivery networks and recommender systems, where decisions are combinatorial and feedback is binary and nonlinear. So let us begin with the core challenge. In many systems, we select a subset of items each round. See a list of recommendations or group of servers in the CDN. This is typically modeled using combinatorial multi-arm bandits, or CMAB in short. But there's a twist. Real-world outcomes are often binary. Click or not click, success or failure. And they depend non-linearly on features, often modeled by a logistic or what we know, the sigmoid function. So as you can see in this figure, this function is really complex. Small feature changes can cause large shifts in probability near the decision boundary, but flatten out elsewhere. However, some AB models typically assume linear rewards. Logistic bandits handle nonlinearity, but only for single-arm selection. So our question is, can we really design a framework that supports combinatorial actions and captures nonlinear binary outcomes? Our answer is yes, and propose this combinatorial logistic bandits framework, or ClogB in short. ClogB is the game between a learner and M arms. Each arm has a feature vector, and its binary outcome is governed by a logistic function of that feature. So in each round, the learner selects a superarm, a subset of arms, and observes the binary outcomes of those selected. The reward is the sum of these binary outcomes, and our goal is to select the cumulative regret over T rounds. But ClogB is really hard for three key reasons. The first is that the number of possible subsets grows exponentially. Exhaustive search is intractable. The second is unlike linear models, logistic regression has no closed form MLE, which makes the estimation and uncertainty quantization really difficult. Finally, we really need to keep a balance between the learning and computation efficiency trade-offs and control the large factors regarding action size k and the linearity level kappa. So existing logistic bandit methods don't scale. They explore both the arm set and the parameter space exhaustively. So our solution is to propose UCB-based algorithms that balance exploration and exploitation efficiently. So here is how it works. So first, we estimate the city hat using logistic regression on past data. Then we compute UCBs by adding exploration bonus to each arm's estimated mean. And the design of the bonus results in three different algorithms, which are variance agnostic, variance adaptive, and localized with burn-in stage. Finally, we use an efficient combinatorial solver to choose the best superarm. Our theoretical results shows that the variance agnostic C-log UCB is fast and simple, but with slightly higher regret. The variance adaptive VA C-log B UCB has tighter regret using projected MLE, but expensive due to the non-convex projection. So eventually we propose EVA C-log UCB, and for time invariant features, we use the burn-in phase to avoid projection cost, achieving the best of both worlds. So across synthetic and real-world datasets like CDN and learning to rank, our methods outperform strong baselines like VA square, C-square UCB by over 70%. And the C-log UCB and the EVA C-log UCB are quite computationally efficient, and while the VA C-log UCB achieves the lowest regret. Okay, to sum up, we introduced the C-log-B framework for online learning with combinatorial actions and logistic binary feedback. We designed three UCB algorithms with different trade-offs, provable regret bounds, and strong empirical performance. Our methods really can apply to diverse systems like ranking, CDN, and adaptive routing. Okay, thank you so much for listening. And for any questions, please see our paper.